To learn hardware security, it is important to understand how hardware is built first. In this set of slides, we will briefly review the fundamentals of digital logical design. We will talk about digital systems, and we'll talk about the design and the synthesis of such systems. We will start with how to specify such systems, how to implement digital systems, and how can we optimize such implementations. And we will use examples from both combinational logic and sequential circuit to demonstrate these procedures and concepts. And finally, we'll talk about the don't care conditions. These are the conditions that have played a crucial role in terms of the system synthesis and optimization. And don't care conditions, they can also cause security vulnerabilities. However, when used properly, don't care conditions can also provide us a unique opportunity to build more secure, more trusted systems. A system can be viewed as a black box. Where we have the system here, it takes input and generates output. And the input-output pair, what their relationship is what we call the functionality. And the system is used to model the real world and then trying to get reasoning behind all these phenomena. So we know real world is analog world, so which gets captured by this figure here. Both the input and output signals, they are analog signals. And this captures precisely what happens in the real world, and then this x-axis is the time. And however, computer doesn't like these continuous values. So what we have done is we digitalize all these signals. So this is a digital signal here, where the values take only discrete values. 1 level, 2 level, 3 level for this signal, and then 2 levels for the other signal. So this becomes a digital signal. And also based on when these signals can change according to time t, we can put digital systems into 2 categories, the synchronized systems and asynchronized digital systems. In the synchronized systems, the signals can change its value only at the discrete time, which is normally periodic, which is what we call the clock. At each clock, they may or may not change, and then during the clock, the signal stays at constant value. And in the asynchronized version, the value of input and output can change at any time, but however, they are restricted to these discrete values. The last concept we want to talk about is the difference between combinational logic and sequential logic. So in a combinational logic, whenever you take a given input combination, you always have the same output, no matter how many times you run this system and when you feed this input to the combinational logic. But for the sequential system, the input and output pair may not be unique, which means for the same input, your output may not be the same, may be different. So why that is the case? That is because inside the sequential system, there is a unit called memory elements. The output depends both on the input and the current value of the memory unit, which means the combinational logic inside the sequential circuit will take input from primary output and also internally from the memory units, and then use this to evaluate what will be the output. And then meanwhile, it's going to update the memory units. So now we talk about how to specify a digital system. The specification of a system is a description of its functionality and other characteristics that is required for its use. So when people specify digital systems, normally they go from high level to low level or binary level. And we have mentioned about the systems. Normally they take input from real world. And real world is analog. And so the first step we need to do is we need to convert these analog signals to digital. And then for digital signals, sometimes we still have to do an encoding. So this is the input encoding. And also when the system output and output feedback to the real world, we also want to do an encoding. So after the computation, we got the binary output, and then we need to convert it back to real world. It can be digital, can be analog. And in the middle, we need to determine how we can get output from the input. That is the one we call the Boolean function. This function determines, given input, what will be the output. And normally these Boolean functions will be represented either as a truth table for combinational logic or as a finite state machine, or sometimes we call it a state transition table or state transition graph. These are used to model sequential systems. So let's see a small example to see how we can specify a digital system. So we want to design a system that will tell you whether a given month has 31 days or not. So we think about this. For this system, the input will be the 12 months of a year. So we write a high-level system spec. The input X can go from January to December, which we represented by decimal numbers from 1 to 12. And the output will tell whether this month has 31 days or not. So we can represent this by a single bit Z called 0 or 1. And 1 means it has 31 days, and 0 means it doesn't have 31 days. And the functionality of this system can be represented by this step function. When X is 2, 4, 6, 9, or 11, which means when X is February, April, June, September, or November, it will not have 31 days. In other months, it will have 31 days. And we can easily draw a truth table to represent the same information. The input X goes from January all the way to December. And then the output Z tells you that which month has 31 days, which month doesn't have 31 days. And this is a high-level system spec. And before we can design these systems, we need to convert a high-level system spec to a low-level system specification. And by low level, we talk about the binary level. And in this system, we know the X input has 12 different values, 12 different months. And to represent 12 different objects, we need 4 bits. That is why the input bits will go from X3, X2, X1 to X0. And the output has only 2 possibilities, 0 or 1, so there's only 1 bit for output. So then we can convert the previous truth table to this truth table at the binary level. So this is X at the high level, goes from January to December. This is the output Z, tells you whether it has 31 days or not 31 days. And in the middle, we see the input encoding, where we use the binary encoding. So January, which is 1, is encoded as 0001, and then April, which is 4, is encoded as 0100, which is the binary 4. So the next step we need to do here is trying to figure out what will be the functionality. And remember, before we write the functionality as a step function. And now since we have moved down to lower levels or binary level description, so we need to think about how to rewrite this function at the Boolean level, at the lower level. So what we do is we take a look of the input, the 4-bit input and output. And this is the design phase. So we want to express the output as a Boolean function of the input. And by observation, or by later on we do any kind of optimization technique, we figure out in this case the output Z is X3 complements times X0 plus X3 times X0 complements, which is the same as X3 exclusive OR with X0. Which means that whenever X3 and X0 they are different, the output Z will be a 1. Whenever they're the same, the output will be a 0. For example, here, 0, 1 give you a 1. 0, 0 give you a 0. 0, 1 give you a 1. And 1, 0 give you a 1. Whenever they agree on each other, 1 and 1, they give you 0.